welcome back to our lecture video. Sorry to be a little bit strict today because my hair is pretty long and I didn't have a chance to cut it. Um, but today lecture we will go to AC load line, and remember we went through a DC load line previously. So today we will go to AC load line. So we will see the difference between AC and DC load line. Another thing is remember the main point of all of this is to be able to amplify an AC signal from, let's say, a smaller swing to a higher swing. So we have to be able to analyze the maximum symmetrical swing of our output. Therefore, we will also go through the mathematics for that too. So let's get to it. So the goal of this lecture today is for you to understand the concept of an AC load line and to be able to calculate the maximum symmetrical swing of the output signal. When we include capacitors in our transistor circuit, we need an AC load line in order to visualize the relationship between the small signal response and the transfer characteristic. So first, let's start with this circuit. This is the transistor circuit with an emitter resistor and bypass capacitor at the emitter that we discussed at the end of last lecture. So first of all, we need to figure out the DC load line before we start with the AC load line. So if we go through the collector emitter loop, which is here, we can derive, we can use the K-curve voltage law to derive the relationship of all the voltage and current in this loop. Remember that in DC condition, the CE, the bypass capacitor, become open circuit, so you can let current flow on the way through. Therefore, you can have this equation of V plus equal to the voltage across RC, which is ICRC, the voltage plus VCE plus the voltage across both RE1 and RE2. So it's going to be RE1 plus RE2 multiplied by IE, then plus V minus. So let's use the hint here. If I have IE, I can relate to IC with the beta factor of 1 plus beta over beta. So therefore, I can have an equation of IC equal to V plus minus V minus minus IC multiplied by all of this resistance factor here. So technically, I move V minus over here. I move everything else except for VCE over here. Then I factor out IC because I replace IE with this equation. Okay, there's two things I want you to notice. The first thing is this V plus minus V minus. This is a special case for this circuit. In other regular case and in many cases, you can replace this whole factor with VCC. So technically, you just have to ground this end, supply here with VCC. The second thing I want to talk about is this term of 1 plus beta over beta. In many cases, beta would be a large number, usually 100, 200, 150. So if beta equal 100, for example, you can have this factor to be 100 and 1 over 100. So it's going to be equal to 1.01. So you can estimate this whole factor to be 1 for your convenience. Then you can write the equation of VCE to be VCC minus the sum of all resistance in this path multiplied by IC. So then you can have your DC load line equation to be this. Technically, you just have to move IC term over here, move VC terms over here, and divide two sides by the resistance factor. So you can have the DC load line, the slope of the DC load line to be approximately -1 over RC plus RE1 plus RE2. The reason why I say approximately is because of this approximation. Therefore, since you have the DC load line, you have the x-intercept at our VCC. You can derive your own Q point, VCEQ equal 4, for example. Then you have the slope, so you can draw your load line on the IC, the IC versus VC plot. So next, we're gonna work with AC load line. So same procedure. We start with applying K-cup voltage law on the collector emitter loop, which is this loop. However, remember in this case, the reason why we have this CE capacitor or bypass capacitor is in order to bypass a large portion of the emitter resistor in AC condition. Therefore, when you analyze this loop, what you want to do is you go over up to this junction, then you allow the current to go through here and bypassing this loop. So in this case, you can see we can have IC plus VCE it's ICRC, which is the voltage across here, plus VCE plus IE RE1, the voltage across this path. And also in AC condition, you have to remember to ground your VCC. That's another thing. You can relate that to your small signal equivalent circuit to see that how it works. Now you use this hint over here. You have IE equal 1 plus beta over beta IC. So because if you do that, and remember last time we estimate this to be 1, so now we can do it again. We can estimate this whole term to be 1. Therefore, we can say that IE equal IC. So now we can write our VC equation to be negative IC multiplied by RC plus RE, which is the total resistance up to the point that you plug in your bypass capacitor. Therefore, now your slope is -1 over RC plus RE1. So now you can add your AC load line into your transfer characteristic plot. First thing you can see clearly is that the AC load line and the DC load line meet each other at the Q point. However, the slope of AC load line and DC load line are different. And that difference is attributed to the emitter resistor RE2, which is not included in the small signal equivalent circuit due to the bypassing effect of our bypass capacitor CE. The small signal CE voltage and the collector current response are functions of the resistor RC and RE1 alone. Let's work through one example together. So we have a circuit in here, and what I want you to do is I want you to find the AC, both the DC and the AC load line for this circuit. So let's take a look to see what we have. first of all, you look in the middle, you can see your transistor in here, and basically now you're working with PNP. Therefore, it's given that I give that your VEB on, not BE, okay, is for PNP. Your VEB on is 0.7 volt. You have a number for your beta to be 150 and your early voltage to be infinity. That means there's no early effect in this transistor. So what's next? Now let's take a look at the base. The base, you can see that you have a coupling capacitor. Okay. At the collector, you have a bypass. You basically have a bypass capacitor at the collector, but you also have a bypass capacitor at the emitter. So effectively, what it does is during DC condition, okay, during DC condition, your current will flow through this line over here. Your current will flow from top, follow this, and go in here. This is in the DC condition. However, in AC condition, what happened is your current will go through this loop. Okay, this one and this one will be bypassed. So let's start with the DC load line first. So what do we have here? If we go to, we work on the collector emitter loop. Collector emitter loop in here. Okay. So what we can have is basically we can we can relate all the voltage together, just like the previous case. So we have V plus equal the voltage across this resistor plus VEC plus the voltage across this resistor plus V minus. Okay, so now we do some magical arrangement to have VEC. Okay, and then we did that before, but what I want to notice to you is in here we basically replace IE with 1 plus beta over beta IC. Then we estimate this whole term to be 1 so that we can have this equation here. We plug in the number for RC and RE to have VEC equal 20 minus 15 IC. Then now we can have the load line equation of IC equal 20 minus 1 over 15 multiplied by VCE. Now we need to find the Q point before we move on to figure out where's our AC load line. So first of all, I decided to go through this process a little bit slower so that I can remind you how to find Q point. So first, for PNP, you want to do it a little bit reversely. For NPN transistor, usually we start from base and we go down to the we go down to the emitter. But for PNP, you want to go in the other direction. So apply Kirchhoff voltage law in this path or this loop. Okay, we start with V plus. Okay, V plus is going to be equal to the sum of the rest of the voltage. So voltage across this resistor, add in here IEQ multiplied by RE. Then you add VEB on. Then you add the current across this resistor, IBQ multiplied by RB, and you ignore this portion since you already have a coupling capacitor in here. In DC, this portion will be open circuit. So now what you want to do is move this one here for IEQ, basically the quenching point emitter current. You convert that into IBQ using the equation IEQ equal 1 plus beta IBQ. Okay, that ratio 1 plus beta for emitter and base. Then what you do next is you factor out IBQ in here. Okay, so look at this now. This is a constant. This is a constant. It's given. Everything is given. So now you can find your IBQ, right? So you move everything on one side. You keep IBQ. You plug in all the numbers. You have your current, the base current at quenching point to be 5.96 microampere. Then for Q point, this is the key. Once you figure out one Q point parameter, the rest of them are very easy. Technically, you just have to plug in the equation and you get the result. So what do we know about ICQ based on IBQ? Is one beta difference, right? So you multiply beta for IBQ, you have this 0.894 milliampere. Same thing to find IEQ, the emitter current. You multiply for 1 plus beta, and you have 0.9 milliampere. Finally, for BECQ, technically previously we already derived an equation for BEC, right? Now you just have to put the Q point in all of the parameter. So we put in Q for VEC, so it becomes VECQ. For IC, it will become ICQ. And you plug in the rest of the number, then you will have 6.53 volt for VECQ. So first of all, if we consider one of the capacitor acting as short circuit, okay, we can convert our original circuit into the equivalent happy pi model. On the current direction and voltage polarities in the happy pi equivalent circuit of the PNP transistor are reversed comparing to the NPN device. So to begin with, we need to figure out the happy pi parameter, the small signal happy pi parameter. So technically just plug in all of the equation that we done before. We can figure out R pi, GM, the transconductance parameter, and the output resistance. However, because since we don't have any early effect, so output resistance can go to infinity in this case. So next, we try to figure out our output voltage. So output voltage is basically the VCE here, as you can see. So you can also analyze this loop. Okay, look at this loop. You know that VCE equal to the current. Okay, this current flowing here multiplied by the parallel resistance. Okay, the two parallel resistors here. So RC parallel RL multiplied by GM and V pi. And since we have GM V pi is actually equal to IC, so we can replace this term GM V pi with IC. Okay, noting that now I'm writing the equation for VEC, not VCE, so I need to put a minus sign in front of it. So finally, our load line is VCE equal to minus IC RC parallel RL. Therefore, you can see the slope of our load line to be 1 over RC parallel RL. One of the comments I want to make is that in small signal equivalent circuit, a large 10 kilo ohm emitter resistor is effectively shorted by the capacitor CE. The load resistor RL is in parallel with RC as a result of coupling capacitor C2. Also, the slope of AC load line is substantially different than the slope of DC load line, and I will show you the load line right now. Okay, as you can see in here, we just plotted out our load line for AC and DC. So first, we figure out the equation and the slope, right? So we can plot out our DC, then we put on the Q point, then we figure out the slope for our AC load line, and we can draw out that slope. As you can see, because we effectively put in a coupling capacitor on both emitter and collector, so our load line, the slope of the AC load line is differ significantly, as you can see, in comparison to our DC load line. Okay, so finally the last topic is the maximum symmetrical swing. So the goal is, let's go through an example, and let's find the maximum symmetrical swing in the output of the circuit that we just analyzed in the example. So to start with, we actually need the load line that we just found in here. To start, basically, we have to see how does the collector current swing. So the collector current can swing. Let's consider one side of the swing first. So usually you want to start around the Q point. If you start at Q point, the negative swing can swing down all the way to 0, right? Therefore, the maximum possible symmetrical peak-to-peak for the AC collector current can swing down from 0 up to 2 times of this Q point. Therefore, you can see delta IC is equal to 2 multiplied by 0.894 equal to 1.79 milliampere. So next, let's consider the maximum swing for VEC, which is our output voltage in this case. So delta VEC on this line. Technically, what you need to do is it's actually the same swing. The main difference is because you have to convert that with the slope. So you divide it for the slope, right? So you divide it for the slope. So you multiply for RC parallel RL. So you have 1.79 multiplied by parallel 2. So you have 2.56 volt. Therefore, we can have an equation for instantaneous collector current is IC equal to ICQ, which is this point, the Q point of IC, plus half of the swing. So that's it for our lecture today. If you have time, you can try out the example 6.11, but if you have time, it's totally optional. Next and final topic of this week is multi-stage amplifier. So we will go away from the textbook a little bit, and discuss different topics because it will be needed for your laboratory later. This is the end of our lecture today. I hope you guys learned something, and I will see you guys next time. Bye.